And everybody else. Robert, Jim, Tony.
Was it Tom?
Jay.
Jonathan.
Jonathan.
Russell.
No.
So what are you doing here, Robert?
I'm demonstrating this.
Yes, that's you're not here.
Originally, we dropped on top. Everything's the same on the front.
That's
Right,
Bill.
you can move stuff around. So then you can start moving stuff around. So what we really want to do is probably have one around front even. Here.
Oh, yes.
And then set it out.
Didn't know if you would.
What I wanted to do is, I mean, I have. It's just that I couldn't discuss it, you know.
No, I just
Well, this is two.
I am Scott. Why? But I envisioned this gray hair.
Wise
Like Zeus.
Okay, I got it now.
I didn't know you were worship.
Let me see how close I can get in.
First you
Turn sideways. Yeah, it's turn sideways because it's focusing on your shirt.
Oh, I
That's strange. I can't quite get it.
Want to go farther?
Yeah, right. I've got it right there. Yeah. Okay.
Phil, are you going to stand behind the computer?
Oh,
Yes.
Okay, then I'll.
That's the spice cube. The problem is this guy seems to stick out of color. So you have to stand right the first time.
You're on.
Jim, are you going to join us?
Yeah.
Maybe you want to.
Okay, my name's Dave Koski, and I've been working on five-fold polyhedra for about 8 years. I was primarily inspired by the golden proportion, which is infused in practically everything that I'm dealing with that's on the table here. So I guess the thing that I have to contribute to five-fold polyhedra is that one can take Buckminster Fuller's T module or the volume of it and rationally account for the volumes of all the five-fold polyhedra. So you can use a whole number of integer values of T modules to express the volumes of all the five-fold polyhedra and therefore the relationships between them. I don't really want to get into a discussion about the golden proportion itself right now. Is there anybody who needs to be primed on what the golden proportion is somewhat, just to get an idea of the basics of it? I don't need to. All right, I'm just going to show it for the sake of discussion. And I lost my note. And the question is, I would say related to the square root of 5. It's major and important connection. And if you put two squares next to each other, you have two 1x squares, and you run the diagonal here, that value is the square root of 5. The golden proportion is basically a cut on a line as to, I never say this right, where the larger is times the, I'm not going to even try to say it. Okay, so I'm going to take the square root of 5 length here, and I'm going to section it at a value of 0.618 and a value of 1.618. 0.618, and this is rounded off, add up to 1.618 equal the square root of 5. And So then the 1.618 is equal to the square root of 5 plus 1 over 2. And 0.618 is equal to the square root of 5 minus 1 over 2. If you multiply the 0.618 times 1.618, you get the value of 1. So they're, in a sense, they're inverses of each other, and they are, okay, I'm not going to go into a big discussion about this, but there's much significance given to the golden proportion in nature and the nice mathematical period and all that other stuff. It's also involved in the 5-point star and pentagon, where there's a smaller pentagon and that's inscribed inside of a pentagram inside of a larger pentagon. This can keep on going indefinitely. And if you give the value of the smaller pentagon at 0.618, then the value of the edge of this star is 1. So therefore you add those two together and you get the value of the next pentagon, 1.618. So the numbers work very well together. The interesting thing is that they can be translated into three-dimensional volume also, the relationships of golden proportion. And so you can construct polyhedra from those values, and then the volume enclosed by those numbers, also the relationships of the volumes start to have the golden proportion values. Boy, so many places you can start. In the 80s, it seemed that there's a lot of interest in five-fold symmetry because of quasicrystals, and they've been working with primarily two rhombohedra hexahedrons that combine, and they do fill all space in certain orientations, but they also are atomic models of a metallic crystal that was actually discovered. The interesting thing about these two forms is that the value of their diagonals is 1.618 to 1, or you can say 1 to 0.618, and so on. But that their volumes then are 1.618 to 1 also. The volumes are generated from the surface characteristics.
What are those called?
Those are called, I guess, the fat and thin rhombohedra in quasicrystal language.
And one of them is just the same as the other one, flattened out?
Well, yeah, there's a different orientation of the 6 diamonds that make it up. So here they're on the acute angles, here they're at the obtuse angles. And just, so it's the same 6 diamonds organized 2 different ways, and it encloses volume relationship 1.618 to 1. So there's been a lot of work on those 2 forms and five-fold symmetry. So I happen to be working on golden proportion on my own and discovered these 2 shapes kind of simultaneously. It was kind of interesting that it happened that way. But I think I got a different view of the whole geometry because I was dealing with Buckminster Fuller's rhombic tricontahedron and the T-module. And this is a rhombic tricontahedron, and the surface has been subdivided into 120 lowest common denominator triangles, LCD triangles, that's what he calls them. And if you project from the 3 points on the triangle to the origin, you create what is called a T-module, Fuller's synergetics language. I colored the diagonals of this rhombus, of the rhombuses on this rhombic tricontahedron to demonstrate that the red lines form an icosahedron and the blue lines form a pentagonal dodecahedron. So they're both inscribable within the rhombic tricontahedron. I, physically demonstrate that by taking this icosahedron of the volume of this proper size, and it does fit in there. I'm struggling now. And there's also the pentagonal dodecahedron that fits inside of this tricontahedron, the blue edges.
Yeah, can I just say something?
Sure.
Just so it might make it easier for people that don't know much about this is that the reason why they fit in there so perfectly is because the Icosy dodecahedron, which combines both of the pentagonal dodecahedron, yeah, exactly, is the dual to,
Of the-
yeah,
right. That's
which
the point.
just means that it has, you know, faces and vertices inverted.
I'm gonna shift a little bit to try to cover a different area, an area that I'll come back to ultimately to what I've just been discussing about the T module. Let me finish up the T module. You can take Buckminster Fuller's T modules and generate the fat and thin rhombohedra by combining them in such a way to make the fat one, and I lost the thin one. Nope, that's not it. I don't know where I did it. Sorry. Okay. Anyway, I've done other presentations on that subject of the T module itself. Oh, here it is. Okay. So here's the thin rhombohedra. I've used smaller T modules to fill in this gap here. And what I mean by smaller is I've actually scaled the T modules by a factor of the golden proportion. If this edge of this T module was 1, then this one would be 0.618. And so therefore the volume is 3 powers less, or let's say to the -3. If this is a volume of 1, this is to the -3 lower of the volume. Actually, it's 5 to the -3 if this is 1. But and also within inside this fat rhombohedra there's some space, and hasn't been resolved inside there. But if one has 6 of these and these have been enlarged, these are T modules of different sizes descending down that ultimately do fill that in, but it's impossible to completely model it. But they do infinitely progress to smaller and smaller sizes based on the golden proportion cuts. So I think that's kind of a unique approach to the fat and thin rhombohedra. I haven't seen that published yet, and I think it's because of Fuller's T module that I utilized and had a lot of faith in it, and it worked. I'm going to go over to what I call just about principles of hexahedrons that will bring me into the other area that I've been working on. Here's a cube octahedron, and the way I've made it is I've taken a cube and I've taken what I would call a tet-octet combination of a cube in such a way that you take off a tetrahedron on this side and a tetrahedron off this side. It is an octahedron, and if you assembled 8 of those, you would have this cube octahedron here. And that's just made up of 8 of those, 4 here and 4 here. Now I've made the octahedron inside. So you can see it, such as this network here, you can put cube octahedron next to each other and you'd have an octahedron here in the spaces. So if we're all familiar with the jitterbug, when you collapse the struts, basically this triangle is rotated into this toward the center, forming the octahedron inside, is what happens there. It's kind of nice to be able to make cube octahedron from the same, actually it's a 45-90 triangle. It's just cut up squares, it's kind of easy. So that demonstrates one way to slice a hexahedron or a cube, and that has a tet-octet configuration where this would have a volume of 1 if this had a volume of 4. That integrity of tetrahedron to octahedron is maintained from regular tetrahedron to octahedron volumes are 1 to 4 also. There's a couple other ways you can do that to a hexahedron. You can also take 4 of those tets off and you'd have a resulting tetrahedron inside. That's another way, and then this would have a volume of 2 to every one of these, because there's 4 of these, and you end up want to have to end up with a volume of 6. There's a couple more ways you can do it. Slice up a cube with this into 6 units, so to speak. I didn't make the complete model. I have half a cube here, sorry to say, and basically you cut it from corner to corner down through the center of the cube, and you have these forms here, and there's 6 of them make a complete cube. And the last way is kind of a little different way. You need 3 of these tets here. And see, it gets kind of anti-gravitational real fast. So anyway, I'm making a cube, believe it or not. And there it is. So that's the cube, and I have 3 of these tets here, and 3 of these here. And they're all sharing the same faces. Not all the same, but you know, they're sharing faces and things like that. So one can take the ways you can divide a cube into those 6 equal parts into the fat thin rhombohedron. One can still apply these principles where you can go along this diagonal and pull off the tet, and pull off the tet off the bottom and have an octahedron. And you can do that here also. You can pull off the tet off the top, the tet off the bottom, and have an octahedron in the center. But you can also do that on this line too. You can pull a tet off of here, have an octahedron and a tet down here. And it maintains that 1 to 4 volume. You can also apply the other ways of cutting up the hexahedrons. And in doing so, one generates, you cannot assemble those forms from the original T module, Fuller's original T module. And Fuller's original T module has irrational surface angles on it. And when you slice in this way, you're getting an equilateral triangle, so therefore the T module doesn't have surface angles of the same, so it can't possibly, T modules themselves cannot possibly model that form, even though the volume is maintained. So then we need other T modules is what we need, or some kind of equivalent. And they do exist, and they're not too far-fetched. First of all, we'll go back to this principle of hexahedrons and apply it to a golden cuboid, which is, I think, a fascinating form because it's made up of four golden rectangles, 2 on each end being the smaller size and then the next larger size gold rectangles. And one can take 4 T modules, Fuller's T modules, off the sides, and you have this tet, which I think a person named Tel Anderson has demonstrated is called the Q module, and it has a volume of 2 T modules. I haven't really went into the guts of this one yet, but we can also take this same golden cuboid and cut it a different way. So we have 6 parts, equal tetrahedrons, volumetric equivalents, and you'd have to first cut it on the diagonals and then also go from one corner to the opposite corner. And what you get are 6 tetrahedrons that have the volume that is the same as the T module, but their surface characteristics now allow for angles of 60 and 30 degrees and 45 and 36 degrees. These are surface angles that are in the pentagonal dodecahedron and the icosahedron. So these are actually kind of neat forms. They all have 2 faces of the original T module plus other faces that have surface characteristics of icosahedrons and pentagonal dodecahedrons. And one can express the icosahedron and the icosahedron and pentagonal dodecahedron. These all have these surface characteristics that are have rational angles on their surfaces, and they can't be modeled with the original T module, but they can be expressed in T module volumes. Like this would have 84 of one size and 12 of the next, so it would be 84 of, let's say, the yellow size and 12 of the green size. But then modeling it is a different story. First of all, there's a lot of fun that you can have with these. You can create these wedges. First you can create, like, they almost remind me of peaked roofs or something. You have this wedge here, which is taking that slice direction, and you can also create this wedge, hexahedron. So like another peak drift, and then you can also generate one last wedge, which is a sharp one, such as this.
Yeah, I was just thinking, it's like selecting something that's really like
Slippery.
yeah,
Um,
like a magician.
now you can combine 4 of the same of these modules with a left or right handedness. You need 2 of each, 2 left and 2 right, and you can combine them and form. I only got 2 of each, so I'm not making full form, but I do have them. Okay. You can make these forms here. These are really nice. These 3 tetrahedrons can be formed. They have the volume of 4 T modules, and they 4 of one of the 3 different ones, and 4 of another one, and 4 of another one. They have 2 equilateral triangles, and then what is part of a pentagon here, and it's a tetrahedron. And then we have another tetrahedron, 2 equilateral triangles, and what I call a star point, which is part of a pentagram.
Now, what are the angles of these?
Well, this is a 60, 60, 60, and then this is a 36, and these are 72 each here. And you can put them together, and that's your Penrose tile. So that's like your thin Penrose tile, and then this is your fat Penrose tile. So,
Wow.
what also is really neat about this is that 5 of these edges on this form and 5 on this form are edge 1, and then the other edge is either 0.618 or 1.618. These all 3, by the way, have the same volume. So you've taken a regular tetrahedron, let's say, and you expanded just one edge to 1.618, or shortened one edge to 0.618, and they have the same volume. And in this one, you've expanded one to 1.618 and one to just 0.618.
The
So
Penrose,
they-
the
all-
Penrose tiles are in 2 dimensions, though, right?
Yeah, they're in 2 dimensions.
And this is
I was just showing that this is a fat Penrose tile. This is
Yeah.
a flat surface here.
That's really interesting.
So, for a long time, I didn't think you could combine these to make icosahedrons and pentagonal dodecahedrons and things like that. I kind of gave up on it because it was hard. I didn't want to make a lot of models and stuff. But I don't know how, sometimes it just comes to you, all of a sudden it shows up. That's interesting. Where do I go from here? One thing that's neat about this is that they remind me of almost like 3 bones in the inner ear or something. This feeling I get for them. They have this way of combining, and they're really parts of golden cuboids that form there, but they kind of have these really neat. That one's cut for a reason. But there's a lot of neat things you can do with them. I do have more of them. So, Yasushi Kajikawa came out with a paper and some software dealing with 5-fold symmetry, trying to create a hypermatrix for 5-fold symmetry to incorporate 4 quasicrystals and synergetics in general. And he came up with 10 different tetrahedrons. They aren't all of the same volume, but I do have them here, and I'm going to try to describe them. And I'll start with this one here, which is a tetrahedron. It has a star point, and it also has 3 faces, which are half of one of these rhombuses. So if you cut a tetrahedron off the top of here, you generate this tetrahedron. Following that same principle, if you cut a tetrahedron off of the thin rhomboid, you get one of these here. And those are in Yasuchi's paper. And you can take 2 of these from the thin and one of these fatter ones, and you can make a pentagonal surface. So a good way of cutting up a pentagon is at star point to result in side pieces. And then he also ended up with one of these 3 tets here, and he also uses a tetrahedron from a icosahedron. If you project 20 tets from a icosahedron, you have this. Many people have pondered this one. It's the edges are slightly shorter than this, it's usually the first thing that people discover is that 20 regular tetrahedrons can't fit in an icosahedron. So these are shortened somewhat, about 5%. And he also, on the surface, I'm not describing this the best, but if you can cut like a pentagonal tent or pyramid off the top and the bottom, and you can scoop out another one, pentagonal tent, pyramid out of there, and you have a ring of 10 triangles, which are these 10 tetrahedrons here that most of us...
Could you say that again?
Okay, it's hard to describe, but you can slice at this I'm trying to go parallel to the floor, this line here, there's pentagonal surface here. You can pull this out, these are all equilateral triangles, and you can divide that up. And you can make, what is it, like a pentagonal pyramid. And these are all equilateral triangles on the surface. And then you can also take out scoop out per se is a pentagonal pyramid, but it has not equilateral triangles, but these, actually they're half of these rhombuses here that are in these. And you can put these on top of each other, and those are 4 of the 10 modules, and then you put a ring of 10 of these around, and then you just do the same thing on the, or 5 around, and then 5 more like this, and then another one of these on the bottom, and that gives you an icosahedron. What he did then was then take the halfway point on all the edges and extract the octahedron out, and that created the other 5, so then he had 10 modules. So these are the forms that he can make, I think a 2-frequency rhombic tricontahedron, he can make a dodecahedron, a icosahedron, icosahedrons. He can make a lot of different things. What's interesting is this form comes directly from this, one of these 3 tests here. This is off the surface, it's got the 2 equilateral triangles. And these come from slicing the hexahedrons or the rhombohedrons. First of all, I try to keep my volumes very simple, so I've always relied on the T module, and I've been able to express all these 5-fold polyhedra with the T module volume. So I knew that this had a volume of 4, and then this one has a volume of 6 T modules one side and 2 sides and 2 of the next. So then I went to model that, and one can model it. It's kind of slightly tricky, but take one of these units, you take one of these, this green one here, and one of these, put them, actually I'm not saying that, and then you take half of one of these. And you take the next size down, one of these, slice it in half, put it there, and then you have one of this. This is an equilateral triangle, this is part of this icosahedron. And you put these 2 on either side, and you have that same pentagonal tent or pyramid.
I should just say that in Kricklow's Order in Space, which you may know, he discusses that particular shape, the pentagonal pyramid, and he calls it an icosacap.
Yeah.
But when you have a double pair, top and bottom, it's called a decadeltahedron. And I've been working with this myself, and it's actually very critical to, I think, 4th dimensional shapes.
Well, here's one of these little caps here, and you can take 2-frequency icosahedrons, slice the caps off, and get the icosahedron. You can also take a 3-frequency icosahedron, slice these same caps off, and get the soccer ball or the Buckminster-Fullerene. So that's how they're kind of an important little truncation piece. That's the way I
Absolutely, absolutely.
So I'm able. These have volumes of 4 T modules. These have volumes of 4 T modules. This is 2 of the next size down T modules, and this is 2 T modules. I don't really want to get too bogged down on trying to state that exactly. But so now that I've proven that I can make the pentagonal pyramid, I take 3 of those pentagonal pyramids, like such as this, and then start to all look the same. Here they are. I take half of one of these, slice. It's hard to tell which is the half, but I do take a half of that, which is volume 2 T modules, and put those in there. I'm doing this right. Take one of these, which is the next size larger, let's say. Let's start this one. Take half of one of these.
Very nice.
You can make an icosahedron from T module volumes, and this little somehow I call one of these in. I mean, it's not necessarily real obvious, but it can be done, so to speak. You can model an icosahedron with these T module volumes that have come from a golden cuboid. The whole trick is you have to scale these T modules by factors of 5 up and down. That is the real key part, and I haven't found that type of thinking utilized in modeling or modularizing five-fold polyhedra. They've used what I call static module systems, and they've been able to generate with Yasuji's system whole number frequency increases and decreases, but I've lost probably. Anyway, I can make an icosahedron.
That deserves some applause. Really.
Yeah.
That's
The
remarkable.
icosahedron, right?
Because, you know, if the electron is modeled in terms of an icosahedron as Fuller hypothesized, you know, this is very, very important.
Well,
because it's my opinion that it's the Fibonacci series and the phi ratio that's literally the language that all of the quantum particles speak. So this is real breakthrough stuff.
it does work. Yeah, you can count icosahedron in. I give the value of 100 of one size T module and then 20 the next size down is the value I give it. You can push these modules around. Like you can also say it's equal to 20 or the next size larger than 20. So there's a lot of different ways you can express, but they are whole number values, and they are modules. But the whole trick is when I say next size down or next size larger, that's the difference, is that there's this dynamic increasing or decreasing of the module itself involved, which I think is necessary, because it seems very rational once you allow for that aspect.
When you're talking about the size, the next size,
Yeah.
what we have is a series of
Yeah.
so-called solids, as we have the solids which are related to each other in some sort of proportion. And we look upon the solids and nothing's in between. The Buckminster fullerene is called a quasi-crystal because it seems to be an in-between state between one and another. How do we actually define the states? Because there seem to be static states and transforming states.
Yeah.
I assume that everything, all the systems you're talking about units, and you say you lock in at this particular point in the thing because it has a certain proportional relationship. But there's always I assume nature will always transform it in a different way. So the issue seems to be for human beings is to see these static sort of states that we just say at a certain proportion. What is actually happening in that state? Is it the locking of a lattice or something? Do you feel that these lattices lock at the golden proportion?
I go back to the jitterbug, and I think that the jitterbug transformation allows, let's say, a statically locked. This is just all armchair theory. That when you go to the icosahedron, it allows matter to rearrange in let's say a golden proportional matrix. Matter is allowed to unlock from other and not go chaotically somewhere else or just go out of the system, but it can, like, if you create a quasi-crystal, it's been molten, and they've locked it at 1,000,000 degrees per second. They lock these atoms in this arrangement, and then all have this golden proportional structure. I think that I'm going off base here. That the atoms are able to go through space within a five-fold matrix. That's where they're able to change, and then once the heat is reduced or whatever, then they can lock back into a static shape. I know that it's a continuous process, but I think that is once it hits the golden proportion state, then it's able to move about. That's just my feeling.
Is that Is that temperature range also a golden proportion of some sort? Frequency?
I don't know. I'm not very, I'm just a geometry right? That's all. I hypothesize about all this other stuff, but I don't really know what happens.
Yeah, well,
I get flexible.
I think that it's fair to say that the golden mean is somehow, what Fuller would call a mass-demass, breakpoint. That because you have the E module and the T module, and that very, very thin space in between, that's the difference between, the bubble intact and the bubble bursting. The difference between gravity and radiation. So that somehow, well, I have a friend by the name of Dan Winter who's done a lot of work with this, and he thinks that the golden mean is sort of the interval within space-time. It's like a zero phasing, so that on either side of the golden mean, this is where things become mass and where they become, pure energy.
How does that relate to just work to particle and wave?
How does it relate to particle and wave? I'm not really too clear on particle wave stuff myself, just because to me it's just a difference of a 90-degree perspective. You can look at a wave as being, a spiral that goes in like this, or you can look at it from a different angle, where it goes out like that, and somehow the collapse of the state vector might just be, a 90-degree shift of perspective. I mean, but that would be in terms of how consciousness itself is operating.
I mean, I understand this is what you're saying. It's quite an interesting statement about 90-degree shift in consciousness.
Okay, a couple kind of crucial forms can be made up from these shapes, and one of them is what I call a star point pentagonal pyramid. It's got the star point. There's 5 star points, and there's a pentagonal base, and there's a star point tetrahedron. And it's really that model Yasushi made that I just talked about, and you add this form onto it, which is this green one. Anyway, you can make this star point here, tetrahedron, and what I call star point pentagonal pyramid. And it's made up of 4 of these T modules, and then one of these split in half next size down. Because if it was the same size, it would have been this one here. So I can take the next size down. This is like the relationship. Split it down the middle, which you can do because it's long. It's a cutting line, so to speak, and then you make this pentagonal pyramid. What's neat about this is you can take 20 of these tetrahedrons and place them on a
20?
20 of them onto an icosahedron. I have the next size down, and you can make what is, I guess it's called great stellated dodecahedron. And it actually, if this is this volume to this volume, this is 3 times larger than the icosahedron. Exactly. It happens to be like 3 icosahedrons make this form. So, then you can take this pentagonal pyramid and put it on the faces of a pentagonal dodecahedron. I don't know if we have that. And you can make what is, I think, called the small stellated dodecahedron. And it's just 5-point stars, all in second 12 5-point stars, which is also this one, but they're arranged a different way. So, now we can make the icosahedron out of these units, and then therefore we can make this stellated tetrahedron, so then we can make this stellated form here. But one of the key figures we can't make yet, I haven't shown yet, is the pentagonal dodecahedron, which is one of the 5 Platonic solids, so we should be able to make it as fundamental. So you take this stellated form. There might be a simpler way to arrange it. This is a little complicated. There's an icosahedron inside here. We've already modeled that. Then we've modeled the tetrahedrons, and we put 20 of those around. we take the, we're up to this size now, we can place them in like this. But I'm going to make it a little different. I'm going to take that out and take 5 of these forms. You can place them in these valleys real nicely. And then you can, there's actually 30 of these valleys, so you need 30 of these to cover the whole form. And you take these pentagonal pyramids that we've been talking about from the icosahedron, and they fit right in there. And that makes your dodecahedron. There's probably a simpler way to do it, I just haven't figured it out yet. There's a lot of times these smaller modules are aligned in such a way that a larger module just presents itself out of the structure. So inside of a pentagonal dodecahedron is this smaller icosahedron way down inside there. So that shows the pentagonal face there. I'm just trying to... Anyway, so now we can make that, and since we can make this pentagonal point here, we can place that on top of here, it's going to fall down, and we can make what you call Kepler's small stellated dodecahedron here. You can do that at all these different points. Okay. So now we can make icosahedron, pentagonal dodecahedron, and both these stellates. There's a really interesting thing I'd like to talk about now. You can take these two rhombic forms, which are made up of these rhombuses, and they're made up of T-modules. And if you simply give this a value of 1, this would have a volume of 2 times 5 to the negative 1, or 2 times 0.618, which is 1.236 or whatever. But anyway, you combine the volume totals of these two, and that's the square root of 5. If you add these two up nicely, the square root of 5, which is what generates the whole blown proportion. Then, if you... This is really... I really like this one. So, hopefully I can demonstrate this. 20 of these fat rhombohedrons combine to make what I call a stellated tricontahedron. So there's more than one way to cut tetrahedrons out. So if you cut 3 tetrahedrons off that stellated form, you'd have this star point tetrahedron revealing. And that would be, and if you took those 3 off all the way around here, you'd have this stellated form left. And this is exactly 1/2 the volume of this. Exactly. So then you take these 60 tetrahedrons you've pulled off all around here, leaving that as a remainder, and you combine them 5 around like this. That fits right onto your rhombic tricontahedron, making this form. So you can subtract these tets from this stellate form, add them onto the rhombic tricontahedron. So when this was a volume of 1 and this was a volume of 1.23606, anyway, these two added up to the square root of 5. We didn't subtract any volume, so these two add up to the square root of 5, these two forms. And this has a value of 1.618, and this has a volume of 0.618. So right here you have like this series of gold proportion, 0.618, 1, 1.618 right there. Then you can take the points off of the stellated dodecahedron and the points off the icosahedron, and you can combine them to make if you combine the 12 pentagonal pyramids and the 20 tetrahedral star point tetrahedrons, you can combine them, fit them around, and actually make the icosahedron. So that means first we have these two equaling the square root of 5, then we have these two equaling the square root of 5, and then we've done one last transformation and ended up with a pentagonal dodecahedron, an icosahedron, and an icosahedron, all equaling the square root of 5. So there's like these 3 different ways you can cut the square root of 5 and generate polyhedron, and think of it as a line being severed in different places related to these volumes. One thing that's been going on with it's really been the motivation for me is to try to rectify a volume of the T module with A and B modules and get it somehow rationally fit in the whole synergetics rational accounting system. And if we take, so first of all, let's go take these out. If we take the vector equilibrium or the cube octahedron, and we can transfer form it into the jitterbug. It all fits in. What if this is edge 1, this triangle, then you have a spheroid 2 cube. If you go into the icosahedral phase, this is the corresponding size icosahedra. What has happened to the octahedrons that are all around it? They have all had to open up somewhat, and they have opened up to this point.
Can you say that again? I didn't get that.
When in this whole thing here, when you start to compress and go from cube octahedron to icosahedron, the octahedrons have to open up somewhat.
Okay.
So that when this is all a bunch of icosahedrons, what happened to those octahedrons? And this is what's happened. They've opened up to this point where there's actually star points. So there's a nice golden ratio right there on the star point. And 8 of those fit around the icosahedrons. But also, there's another tetrahedron that exists, and it happens to be one of these 3 green tetrahedrons, this one. So we'll open this up because this is also going to surround. I like the way that works, yeah. But you can surround the icosahedron with the same octahedron. Now this is the cube that the icosahedron fits in. And the important thing here is that the cube has gotten bigger from the cube octahedron to the icosahedron. You can see that the edge. So in the whole lattice of cube octahedrons, each cube is bigger, so the actual space, this whole thing is taking up larger space when it goes into the icosahedron. So it's kind of hard to compare the A and B modules that make this form to this form because there's been an increase in volume in the overall system. The last thing is I was going to show that these tetrahedrons have to fit into these spaces here, and that'll hook onto the next cube, so to speak. So it's kind of, so in the in this expanded octahedron, these forms, there's 6 of these sitting mirroring that, so to speak, and then the dihedral angle of the icosahedron can mimic this one here. And since this shape's in between these, that's why I call them like the bones in the inner ear. This corresponds to the icosahedron. This is in between those 2 forms, and this fits right like this. There's like a whole lattice of these things, but then there's regular-sized cubes in between them. But I won't get into that. There's a lot more, and I just kind of quickly ran through it all. But just to give you an idea, I just wanted everybody to know that you can make most of the 5-fold polyhedron now with T-module volumes. I call these like alternate T-modules. They're somewhat permutations of the surface characteristics of the original T-module. But you can still rationally count for the volumes as well. 5-fold polyhedron. And this, to me, represents what I think would be one of the hypermatrices of 5-fold polyhedra. This can be made up of T-modules also, by the way. It's 5 regular cubes intersecting, isolate one color after another. And so therefore you can put cubes on either side. And if you do 5 different cubic lattices, one would be sectioning the whole space into the golden proportion, and it would be subdivided all into these T-modules. And then you can assemble them and you can extract polyhedra of all these different sizes from that. So that's why I think it's part of the hypermatrix. But it's interesting that the original T-module doesn't have the rational angles, and the 3 other alternate T-modules do, and they're kind of related to these 2 forms and then these 2 forms. That's how I kind of see them. These have these surface angles that are all rational, and these don't. And it was that slicing of the rhombohedra that I removed them from here and put them onto here. And then it kind of created the other system. So I'm not sure how the original T-module lattice and the alternate T-modules lattice interrelate, but there's got to be some sort of ultimate hypermatrix from there that probably works or something like that. So basically I'm done with this presentation. If you have any questions.
I just want to go back, because we went through these, and one has a volume greater than the other. So you've got the cube and slightly greater volume than the other one. And you're saying you're trying to get the T-modules to...
Yeah, it's hard to get the volumes of the T-modules to correspond with the A and B modules in some sort of hierarchy of volume. Fuller put a lot of time into trying to get the rhombic tricontrahedron to fit into his hierarchy and give it the volume of 5 tetrahedrons.
So what is the relationship between those two volumes?
No,
One is
well,
greater than the other, so is that the relationship?
well, this cube would be a 1.618 edge, and this cube that this would fit into would be a square root of 2 edge, 1.414 to 1.618, and it does get slightly, pretty much bigger volume-wise. That's pretty much an increase. It's, I don't know how much it would get, like almost 50% or 40% increase in volume in the whole system. So I really don't, I don't spend a lot of time in that area trying to relate 5-fold symmetry to the what I call the 2, 3, 4, 6 symmetries and static symmetries or E and B module forms and things like that. I basically stay within the 5-fold symmetry, and I found that the T module has worked for all polyhedrons. It has been able to, 5-fold polyhedron has been able to account for the volume of all of them. Well, you know what I forgot to show you is Buckminster Fullerene. Anybody, I can make Buckminster Fullerene out of these things, but I can't make the whole thing. I don't have enough money. But I'd like to show you if I have a few more seconds of your time. If you took the surface of a pentagonal dodecahedron, we have a softball here. Here's one. But this is what we're going to make. This requires everything. You take the, everybody's going to maybe have to come up and look at this also because I can't, I have to use the tabletop. But you can take the surface of a pentagonal dodecahedron and add this combination of these units to it. Does anybody think this is like excessive, like too many modules? It's like getting carried away. Sometimes I wonder, but
It just makes me wonder if it can be done more, yeah.
yeah, I wish.
Do you think it countered, and
I think there's a simplification of this. I kind of just ripped through it. I don't necessarily have the ultimate understanding of it. Anyway, I'm just going to model one surface of it. I can't find all the modules. This is really complicated, actually. It would require 6 different magnitudes of modules to actually make it short.
Do you have a table of that, or did you interview?
Yeah, I do have somewhat of a table. Okay, well, anyway. I can't seem to find part of my thing here, but this here, my cheater piece, this is actually 1/3 of a dodecahedron. And it can be modeled out of these 2 modules, but obviously they're very small. But it does fit right in here, which shows the, these are half a hexagon, and this is the pentagonal surface. And this all fits on top of a dodecahedron, which I can model. So therefore you can make the whole Buckminster Fullerene. It's kind of complicated. And then also you can, this is part of a 3-frequency icosahedron, just by putting that on there. I don't know if anybody's been studying Yassushi's work. There's a lot of similarities between the two, but there's some differences. Buckminster Fullerene. really. It's in there.
Would you be able to, and maybe you can answer this also, I guess when I was looking at these and how these fit into one another in a row,
Yeah, they
can
do.
you do the same kind of modeling system with vectors if you scale the sizes and figure out the angles where you can see inside it, so you can see all of it?
Yeah, they do. It continuously goes inside. There's smaller dodecahedrons inside of smaller icosahedrons.
Yeah,
and
kind of
things
like the
that.
Buckminster Fullerene that we did when we.
This is called the golden diamond. Can you see this? This is called the golden diamond because of its diagonals that meet at a 90-degree angle are in the ratio of the golden proportion, being 1.618 to 1, or any of the other factors, 2 successive steps of the golden proportion. This would inscribe inside of a golden rectangle at the midpoints of the 4 sides of the golden rectangle. Okay.
The
So-
Parthenon and so forth.
Right. The golden diamond, there's some interesting things about the golden diamond. If you cut it in half, you have obviously a triangle. It's not an equilateral triangle. It looks as though it is, but the lengths of the sides are about 1/20th less than this base length. The Great Pyramid of Cheops, the Egyptian pyramid, has 4 triangles. 4 triangles. They are not equilateral triangles.
So that's the face of the Great Pyramid?
Yeah, just it's an interesting little thing.
Exactly.
Yeah, there's some things on it. I don't really use that though, but I find it really intriguing.
Well,
I
we're
like
onto
it.
something there.
Yeah, I like that. One of the things that is nice about the golden proportion is that it's an additive and arithmetic and a geometric series that if it's multiplied by itself or added, it's also it's being added to itself. So what that means is if you take, let's say we start with this golden diamond, and if this longer length is 1.618 and this length is 1, and you multiply the longer length, let's say you squared the longer length, you would get 2.618 length and the 1.618 shorter length, and that's equal to adding the longer and the shorter together to give the next longer length, and it's also the longer length then becomes the shorter length of the next diamond. This can progress onward in either direction. The same is true about the golden rectangle. You can take a square out, you have a leftover rectangle, and all the way on down. So with the golden diamond, one can form 6 polyhedra, 5 of them convex or concave polyhedra and 1 convex polyhedra. 2 simplest being a fat and a thin hexahedron. And the astounding beauty and suggestibility of something important about these 2 shapes is that the volumes enclosed by these diamonds are in the golden ratio. So the volume of the larger hexahedron could be equivalent to the longer length of the diamond, or 1.618, to a ratio of 1. So not only do the, let's say, 1-dimensional and 2-dimensional characteristics that make up the shape, not only there in the golden proportion, but then the volume also is there for the golden.
3-dimensional as
Yeah,
well.
3-dimensional stepping process.
Far out.
That's a great thing. It's really one of the kickers about the whole thing.
Excuse me, Dave, I wonder if you could pause for one moment. I really should have another light on you coming from this direction. Because it's kind of, the models are not really being illuminated, they're more like...
It's okay.
If
I
we
don't
could-
have my big models,
okay, if we could...
but here you can form with the diamonds, the fat and the thin hexahedron 6-sided. Then you can take 2 of the thin and 2 of the fat and orient them in such a way that they create a 12-sided form. It's not omnisymmetrical. It's obviously is the equivalent of 2 of the smaller or the thinner and 2 of the fatter hexahedrons. This is an all-space filler by itself. They stack in a kind of a brick-like manner.
And they completely fill with no gaps.
Yeah.
Did you discover those 2 shapes there, the way they meet?
Well, I did on my own, but they're also in quasi-crystal phenomena. And
That must have blown your mind when you found
when
out.
when I calculated the ratio of these 2, then I said the golden proportion is with me to stay. Or something. Obviously, not obviously, but pretty much from principle of, let's say, hexahedrons, is that they can fill all space in the same direction manner. It's as though you distorted a cube, you kind of leaned on it, and it's distorted.
Yeah.
And that would happen with these 2. Here is a 2-frequency hexahedron, let's say, since I've doubled the edges, therefore it's got a volume of 8 of these units. Beauty also of this angle, of this amount of leaning, let's say, then your diagonals then become the golden proportion, is the fact that they have the ability not only to fill all space facing the same direction, but if you twist the orientation 180 degrees, you can also fill all space. This is the type of all space filling system where you have to have a definite center. It's not a space filling system where you choose any center and it's the same everywhere, but you have to have a definite center. And this is a combination of 20. This is also one of the 6 polyhedrons. This is a combination of 20 of the fat hexahedrons. Now, how does this fill all space? Well, take your same cluster of 8, and so if that can fit onto one, therefore it can fit on all of them and fill space, definitely. That will learn on too, because that told me that, wait a minute, there's other ways of doing things. The pentagonal symmetry can fill all space with no gaps, and it kind of opens your mind up. I don't have one of the 6 forms, and it's really, that's okay because it's in the other room, it doesn't really matter, it's not really necessary to the discussion. The most common and omnisymmetrical form is the Raman tricontahedron, which can also be called a planar sphere, in that it is the most amount of faces one can have in a polyhedra of having the same edge length. And I hope I said that right. So I call it like a golden sphere. I equate this to a ball. I interchange the words a lot. I call this a ball. The Buckminster Fuller goes into great depth with this shape. An interesting phenomena of this is that this is like its sister, or an inverse of it. It's not a double volume, by the way, but they fit really nicely together. And you can cluster 12 perfectly about this form. My first thought was that one could then put a second layer of the stellated Raman tricontahedrons around this cluster of 12 Raman tricontahedrons, thus making another form of space filling system, but you can't with a little bit of experimentation. Okay, so
Is the ball the same volume as that?
No, that's exactly where I was going next.
Looks real close.
Yeah, it's pretty close. If the volume of this is 2, this volume is 1.618.
Oh.
Yeah.
Okay.
Most of the volumes have a nice golden proportion type numbering system. The Raman tricontahedron, if this is made of 20 of the fat hexahedrons, this is made of 20 hexahedrons, 10 thin, 10 fat. Unfortunately, I don't have the hexahedrons ready with the tape to show you the interesting arrangement that makes up the Raman tricontahedron of 10 of these and 10 of these. But the core is where you take 2 of each, you make 2 of those and put them like this, then you start to arrange these around it. 1, 2, 3, 1, 2, 3, and then these fit in there. Then you get you start to make the round tricontiheter. Notice the asymmetrical type of combination. Though it's balanced.
Unexpected.
You know, it was interesting. That actually came to me in a flash. I knew that the volume was 10 and 10, but I didn't think it would fit together, but it does. That's in a book by Cox or some guy named Kolowalski. Published that in his book or something. Okay. Anyway, obviously these golden diamond forms have been worked on. There are a number of books. I saw another one tonight. And they're also involved in quasi crystals. Where I feel I branch off, and I'm still looking for some outside recognition of the same somewhere else, is where I took the Raman tricontiheter that Buckminster Fuller goes into it as synergetics, and started utilizing the T module. The T module makes up, the Raman tricontiheter is made up of 120 of these units. This being the origin of the center of the polyhedra, this being the surface, 1/4 of the diamond. And they fit those two. Anyway, there's mirror image complements of that, such as here. You notice I have different sizes of T modules. I'll get into that. This is a cluster, if I did one, 4, making up the diamond. Okay. I can't remember exactly what happened, exactly how I figured it out next, but I started to play with the T modules a bit. And I found that, I have to tear this apart just to make this work better. I found that here's a kind of a clustering of T modules starting to show the combination making Raman tricontiheter. I found that the radii lengths to the, going up to the surface were themselves a gold diamond of the next order. So I calculated the volume of the next larger rhombic tricontiheter in the steps of the gold proportion. I found that it had a volume of the next larger diamond being this size diamond in relation to that diamond of rhombic tricontiheter. I found the volume to be 3 of these rhombic tricontiheters plus 1 of these. So I thought, well, how did 3 of these and that make the next large ones? So I took apart, here's another kind of Raman tricontiheter. So if there's 12 dimples, let's say, on the stellate, and there's 3 of these, that means if to get 12 parts, I divide each one into fourths, and this is now a fourth of the Raman tricontiheter. And they fill in these gaps, making the next larger Raman tricontiheter, illustrating the growth rate. And the next key is, well, how do you make the next larger stellate? Well, there's actually, so also inside of each Raman tricontiheter is a stellated form. And vice versa, there is a Raman tricontiheter inside that stellate on ad infinitum by the direction. Looking at this fact that I now have T modules, Fuller's name for these units making up the Raman tricontiheter, at a 90-degree angle to a T module of this size, I said, well, maybe there's lesser sized T modules, and I started scaling them by factors of the golden proportion. The next increment, like just as such as this, I would just say, okay, I'm going to reduce the lengths by a factor of the golden proportion from this length down to here. And I found that if one was to extract the T T-module that is now created from this second order polyhedra, Raman trigonodahedron. Once called T-module, that T-module is divided. It's divided up into lesser T-modules. And the red T-modules relate to the black on this one, and the green ones, or the faded green ones, relate to these yellow. And then, of course, there's a gap in there, but that also suggests that the fat hexahedron can be made up of T-modules, since this red being the surface there. So the gap has a volume of exactly 1 red plus 1 of the next lesser size. So one can see the self-similarity phenomena here of a unit being subdivided by itself at the rate of the golden proportion. Therefore, each one of these two modules can be subdivided similarly as the overall is being subdivided. And it goes on forever. Plus, it can grow at the same time that it can be diminished. So then I went to make the fat hexahedron out of T-modules.
Oh, yeah.
And there's the famous gap. And this is the gap, once again. The gap can be modeled with T-modules. I have to increase the magnitude for visibility, but here it is. And an interesting, there's more than one way to make almost all these models with T-modules. Once you get into higher frequencies, one can do many different arrangements. That this group of 4 and the next largest size is a group of 4, and there's still a part left over, and it's kind of irresolvable physically to fill that little gap with smaller and smaller T-modules. But it also has kind of a vortexal type of kind of back and forthing of combination. And one must remember that if this is also, all this is fitting right in here,
I was wondering when you're going to fill that gap.
that all of these forms can be subdivided similarly. And,
Right, well, if that ain't self-similarity, I don't know what
and
is.
in other ways too. And it's interesting, at the same time that this gap is being filled, the gap filler has its own similar gap that needs one of what is in my hand and a couple of orders, maybe 2 less, fit in there. Therefore, inside there is another gap, and so on and so forth. The nice thing about it is that all this infinite subdivisioning can be contained and frozen, finited in a sense. And also, that means within this hexahedron is that unresolved, well, physically unresolvable gap, but mathematically and theoretically modelable with T-module gap. Therefore, if one can make this hexahedron, one should be able to make the other hexahedron, the thinner hexahedron out of T-modules. And if one can make these 2 hexahedrons out of T-modules, one can make all the golden diamond polyhedra out of T-modules. Yes, you can do that. It's actually interesting that the thin hexahedron can be made of T-modules, and it can be physically modeled with just 2 different levels. I don't have the smaller size. I have 1. Actually, it's a cluster of 6 that would look just like this, that would fit in there, making the same point on either side. It's an interesting arrangement that can actually makes the same diamond as the surface of the other surfaces of these T-modules. And that fits its point also. That's very nice. So one would say, well, how do you get the next larger stellate from one of these trichromatedrons? If one can have a stellate inside of here, there should be a stellate that can grow out of this, and that's done by just taking that point, which is the equivalent of the triangle we're on here, and placing it on top of here in 20 places, and you have the next larger stellate. And we could take a larger cluster and make another larger round trichromatedron and add infinitum. I think I'm saying that right, but I don't know. Anyway.
Infinitum?
Infinitum? I don't know. Infinitely.
Right.
That's really the root, the core of what I do, is the fact that this one unit, I shouldn't say one, there's a complementary mirror image, plus it requires more than one size, scale by the golden proportion, can fill all space. Some other fun things that it can do, it can, though I don't have a complete model of it, this is like an eighth of a rounded trichromatedron quadrant, let's say, or octant, has 90 degrees there. The cube can be made up, so I'm not doing it right, the cube can be made up of T modules. I don't know why I'm having so much trouble all of a sudden. It can be made, believe me. Which is an interesting net because it shows an unfolded T module is made out of a square.
Son of a bitch.
Yeah. So
That's what we were talking about the apartment earlier. I
Yeah.
was trying to say, how can he do that? Yeah, well, that is unexpected. Huh.
and the folding, you fold these three together makes a T module also.
And those aren't being distorted in any way.
No, it's a bad model.
Right.
But the interior needs different sized T modules, but it can be resolved.
Uh-huh.
And there's all these mathematical equivalents, so I work in volumetric units that are actually the cubes of, or the third roots of the golden proportion. I use numbers associated with these, showing the amount of T modules, and in showing this growth of the rounded trichromatedron, the next larger size, where I had three, I only have two in my hand, the third one, where you take them apart and put them on the surface. If you gave these the value of 3, I mean, each one of these the value of, let's say, 1.618, your next larger rounded trichromatedron is going to be increased by a factor of 5. Therefore, in 3 dimensions, it's a third powering of 5. Anyway, that means the first rounded trichromatedron is 5 to the first power, or 1.618, so that the next larger rounded trichromatedron is going to be 5 to the fourth power. You can add the exponents. The point I'm getting at is that if you're familiar with the Fibonacci numbers, the Fibonacci number sequence, it starts out 0, 1, 1, and you add each successive term to get the next terms. Have you remembered that? 0, 2, 3, 5, 8, 13, on and on. This shows the simplest of the Fibonacci numbers in that the 3 of the Fibonacci sequence is equivalent to these 3 balls, and this has the value of 2, or 2 times 1. So it'd be 3 phi to the first power plus 2 phi to the 0 power equals 5 to the fourth power. One can also write that expression 5 to the fourth power equals 8 phi to the negative 3 power plus 13 phi to the negative, I'm getting lost, negative 2 power. So the numbers 8 and 13 are Fibonacci numbers, so therefore the next, if you're taking the next smaller ball down, if you had 13 of them and 4 of these, because this had a value of 2 and 8 divided by 2 is 4, so you have 4 of these and 13 of these, you could also make the same ball. And then you put the next size down, which is two Fibonacci numbers are 34 and 55. So you divide 34 by 2 and you have 17 of these and 55 of these. And one can make a round tricodahedron. Those are Fibonacci numbers, and they're used in conjunction with the phi numbers. There's an interesting relationship. Anyway, a lot of math books go into phi numbers. This is a three-dimensional representation of those numbers. I like that a lot, actually. It's one of my favorite parts. It's very hard to express in the air. You know, something you want to write down and have pictures with. After that, you go into like more like stuff if you're really into it. I think it's a little more complicated. I don't really know where else.
What's going to happen with that big model that has the black tape on it there?
Yeah.
Pretty one, yeah.
Well, this is a nice one, that's all. It's just a...
That's a complete solid one of those.
Yeah. This is just I don't know, these things have a high degree of variability in their ways of attaching. And they're slippery. They're almost like you can kind of get an intuition of their dynamic quality, just the way that they, you know, that's just kind of, that's reaching for it. But you know what I mean? There's a kind of non-stable gravitational aspect to them, and that makes it hard to do presentations because you need a lot of tape. You know? But what I like about the system is it models growth, in a sense, which goal proportion is related to. It doesn't necessarily model the growth of a tree or anything, but maybe on a genetic level or something. I don't know. Maybe this doesn't have to be limited to an omnisymmetrical presentation. I just have worked with basic omnisymmetrical polyhedra as much as possible to try to get some sense of the generalizations of the system. Obviously, you can branch out and make many different things, like a Lego set with an extra degree of flexibility or pentangle symmetry, more than just an extra degree, maybe 12 times as much or something. I don't know. Also, it uses golden proportion and it moves it into a volumetric relationship. But the forms are made of the golden proportion instead of like this size round ball and this size round ball to make a larger size round ball. I have this polyhedra and this polyhedra make the same polyhedra bigger. You see what I mean? There's a better fittingness. One could take a ball of clay, another ball of clay, and smash them together and fit it into a mold and say you made a bigger one. You know, you understand the concept that these actually fit. So where I haven't seen publication yet is the T modules. And that's a Fuller unit, that's his name. He gave that name to him. And I've seen the whole quasi-crystal phenomenon. I've seen Fuller go into the T module phenomenon, but the meshing of them and the self-similarity, subdivisioning, and the all-space filling quality, and the ability to make a cube, and other interesting things. That's why I keep on going with this thing. Anyway.
So you discovered the ability to make a cube out of it.
Yeah, I discovered this too.
Yeah, right.
Which doesn't seem like something somebody would bother doing. Yeah. But it seems to do something, you know, it has a quality to it.
Yeah. Sure does. It was like I was telling Susan earlier tonight about the Morton salt girl carrying the salt under her arm, you know, the salt container, and spilling the salt. And on the salt container is a picture of the Morton salt girl carrying a salt container. Right. And on that is and this is like the salt container on the salt container.
Exactly.
Yeah.
And there's a quality of connectedness, though there's diversity, potential diversity of assembly of these forms. There is a unity throughout as there's self-similarity. And it goes infinitely great and infinitely small. And I haven't really been able to map this into the real world, except for the quasi-crystal juncture. There's something going on there with the, I would say, the molten state of metal, which has heat applied, which has allowed the ability to become unstable, what we call unstable, and move into a quasi structured realm, and they've been able to freeze that. And there's a relationship, obviously, with the quasi-crystals and the golden diamond. And since this system exists, there might be some sort of fundamental energy